Okay, now we will try to solve numerically the undamped and damped harmonic oscillator problem. So last time we get an exact solution, we solve it by by analytical method, but we also try to solve this using numerically. Remember that in this case both analytic solution we can find, but some complex case you may get to the exact solutions, you only get to the numerical approximation. Okay. That's why what you do is to solve a damped harmonic oscillator using numerical method, first you have to transform a second order equation into a two first order equations, then apply whether you can apply a Euler method or Runge-Kutta method to approximate solution iteratively, updating the position and velocity, and understand that what is you have to understand the Euler method provides basic information, but Runge-Kutta method will get more accuracy. And its solution will be near to the exact. Okay, so these are the steps you follow. The first step is that you have to set up the harmonic oscillator equation, which you have done earlier. So we get the equation m into d square x by dt square plus c into dx by dt plus kx is equal to 0. Here you can look at this. C is called the damping coefficient. So if you put it 0, you get the equation for undamped harmonic oscillator. So the same equation you can use it for damping and undamped harmonic oscillator. Then the second step is to convert to the first order equations. So there are two solutions, first order equations. You can get it. The first one is you can put dx by dt is equal to y2 of t, that is a y1 dash of t is equal to y2 of t. Then this become, we can dx square x by dt square become y2 dash of t. So the y2 dash of t become d square x by dt square. Then you get the second equation. Again, these two equations are first order equations. You don't get the second order differentials from here. Okay, then that's why you get two first order equations. Then what you have to do is you have to apply the Euler methods. We have two first order equations because you have to separately apply the Euler method for this one. Whether you are choosing this one, your Euler method will be this one, and you have two equations you have to apply. Then if you are trying the Runge-Kutta method, you can choose these equations in this step, and finally you have to do the iterations. So there should be some initial position and you have to find a final position. Maybe it's starting from 0 to 1. Then what you do is you have to divide it 0 to 1 into a number of steps. Maybe you can take the steps are 0.1 or 0.2 or 0.5, or you can directly follow 1. And then the step size you have to determine, maybe there should be different edge. Then what you do is you have to go each steps. So if you are starting from 0 and your step size is 0.2, you should start from 0. Then first iteration, then second iteration, this x become 0.2 and you get a y1. Then you have to update this, so that you can do with a for loop, so that you will require a particular position by doing such a iteration. So if you reducing the h a smaller value, your result become more accurate, and it may take more computation for that. So that's all. So now we will try to implement this one in Python. We will write the code and execute it and show how the result will come.